In this series of videos, we will explore the concepts of energy and momentum, two very important concepts in physics. They are important because they are conserved, meaning that they remain constant in general. This conservation gives us greater insight into how energy controls our everyday world. When we think about energy, we think about what fuels our cars, what generates our electricity, or the amount of calories in our foods, and we associate these fuels with energy. There are lots of different forms of energy that you might be familiar with. There is energy from foods that we eat, there is energy from petrol that fuels our transportation needs, there is chemical energy that fuels biological functions in all living matter, and there is electrical energy that runs all of our home appliances, our mobile phones, and much more. There are other forms of energy, such as heat, radiation, and nuclear energy, just to name a few. What all these have in common is that energy is the fuel to do the work. Put simply, energy is the ability to do work. Without energy, we cannot do any of the things mentioned. So let's start then by defining the concept of work. Up to now, we have studied the motion of objects through the concept of force using Newton's three laws. Force has been useful as a quantity that determines the motion. When you apply a force to push at a box, it moves along the floor. You feel tired and you feel like you've done some work. The more you move it, the more work you've done and the more tired you feel. In physics, the word work has a particular meaning to describe how an object is displaced when a force is applied to it. More specifically, work is defined as the product of the component of the force in the direction of the displacement multiplied by the magnitude of the displacement. In equation form, work is written as W equals F dot x, where W is work, F is force, and x is the displacement. Here we've used the capital letter W to mean work, whereas previously we've also used it to represent weight. The two should not be confused. So in this and subsequent videos, we'll use the mass times acceleration due to gravity for weight instead of W. The dot between the force and displacement means that this multiplication is a dot product. A dot product is a directional multiplication where the magnitude of the first vector is projected onto the direction of the second vector. Put another way, it is the component of vector 1 along the direction of vector 2 multiplied by vector 2. This is illustrated in the following example. Consider a boy pulling a cart with some constant force F that is applied at an angle theta to the horizontal. What direction do you expect the cart to move in? You expect the cart to move to the right. If he moves the cart and displaces it by a distance x, then he has done work on the cart. Because the force is applied at an angle, we can resolve the force into its vertical and horizontal components. So what is the vertical component of the applied force? What is the horizontal component of the applied force? So when we resolve the force into the horizontal and vertical components, we see that the component of the force that is in the direction of the motion is F cos theta. So this is a component of the force that does the work to move the cart the distance x. Therefore, the work done by the constant force to displace an object can be written as W is equal to Fx cos theta, where theta is the angle between the force vector F and the displacement vector x. The net result of a dot product is a scalar, since we are multiplying the magnitudes of two vectors. So work is a scalar quantity. So if the component of the force along the motion does the work, then what of the component of the force perpendicular to the motion? The vertical force, which is F sine theta, acts to lift the cart upwards and opposes the weight of the cart. If the weight of the cart is heavier than the vertical upward force, then the cart would not rise. The difference between the weight and the vertical force is compensated by the normal force. However, if the upward force is greater than the weight of the cart, then that force would cause the cart to lift and rise in the vertical direction. So there is vertical displacement. If there is such displacement, then there is also work done in this direction. The force that does this work is the difference between the upward applied force and the weight of the cart. So the work done in the vertical direction is the net force in the vertical direction multiplied by the vertical displacement. Using dimensional analysis, what is the unit for work? The unit for force is a Newton, and the unit for displacement is the meter. So the unit for work is Newton meters. But another name is given for the unit for work, and that is the joule, where 1 joule is equal to 1 Newton meter. In summary, work is defined as a product of the component of the force in the direction of the displacement multiplied the magnitude of the displacement. The angle theta is the angle between the force vector and the displacement vector. Work has a unit of the joule and is a scalar quantity.